I'd like to welcome you to this presentation today at the Society of Petroleum Engineers Annual Technical Conference Exhibition. My name is John Hedengren. I'm introducing Ammon Eaton. He's a third-year PhD student at Brigham Young University. He just finished an internship with ExxonMobil, and he's been looking into model predictive control and other advanced control techniques for drilling automation, particularly with regards to pressure automation. One thing that he's going to be talking about today is, with advanced controls, one concern is that the reliability of those, especially for a drilling start and stop kind of process, is a concern. And so he has some new techniques that he's developed to address the reliability and robustness of controllers as applied to drilling. So I'll go ahead and turn it over to Ammon now. Thank you, Ammon.
All right, thank you, Dr. Hedengren. I appreciate that, and I'm excited to share some of what we've been learning over the last couple of years and some of the results of these simulations, and that we've been doing with model predictive control and with high fidelity simulators in managed pressure drilling. So let me start by addressing drilling automation in general. So this is a kind of a hot topic in the industry right now, and I just want to touch on two of the main benefits. First is the health, safety, and environment. We really want to keep something like this from ever happening again, and with automated drilling and with some of the sensors that are being developed, we can prevent this from ever happening again. We can respond faster to the problems that we're having. The second is the economic benefit. The goal is to reduce the non-productive time and shorten our drilling time, and thereby gain some of that economic benefit. So those are kind of the two main drilling automation motivations. There are more. Now there's a lot of people who are focusing on using PID controllers rather than the advanced controllers. And I want to address that topic for a minute. Our group is focusing mostly on the advanced controllers because of these benefits. So we have here, this is a simulation that was done by a colleague of mine, Juno Park, and we have here the conventional PID controllers, and this top graph is the bottom hole pressure, the bit pressure. This black line is the set point changes that are happening in this simulation. The blue and red, as you can see, are the model and measured actual pressure from the process. And here we're having, this is the mud pump flow rate, and this is the choke valve opening. And in this simulation, we're keeping the mud flow rate constant and just using the valve to control the process with a PID controller. And you can see that it's struggling. It's struggling to actually meet these set points and these changes, and that it's trying to have that control, but it doesn't actually have control over the system. It's not doing what we asked it to do. Now if you compare that to the advanced controllers, you can see the same set point changes here with the model predictive control, and we're using both the mud pump flow rate and the valve opening to control the process, and you can see we're actually reaching our set points and we're able to maintain control over the system. So this is kind of this demonstrates why our group is focusing on the advanced control. We feel like it is a better option for industry, and where hasn't been a precedent set yet with managed pressure drilling automation, we'd like to show the benefits of using the advanced method. Now these advanced methods aren't entirely without problems. They do have some issues, and that's what we're trying to address with this research. One of the issues that can come up is because they use an optimization routine to iteratively solve for a solution, there's no guarantee of convergence of those equations. There's no guarantee that it will actually find that optimal solution. And so some some problems that can come is lost or poor control, and that relates to the reliability of the controller. Also, these controllers rely on a model of the process, and if that model is not sufficiently accurate, it can also cause problems. So to address these challenges, we've come up with an ensemble control structure that will help maintain model accuracy and keep the controller stability without actually interrupting the process. So let me just introduce this structure real quick. Here's a diagram that shows we have here three individual model predictive controllers, advanced controllers. One that uses a high fidelity model of the system, one that uses a lower order first principles based model, and one that uses an empirical model that's purely based off the data. And these controllers run in parallel with each other, taking the readings from the well, and they offer their suggestions to a switching algorithm. Now this switching algorithm currently uses a very simple process. It uses the high fidelity, the most accurate model first. It then will switch to the lower order model, which is less accurate, and then finally the empirical model. And some of the once it decides which controller to use, it will send that back around to the actual process and implement the valve position and mud pump flow rates. So the advantages that come with this ensemble control method is that it is robust and adaptive. It can adjust to changing conditions. Also, one of the inherent benefits of the structure is that you can tune and troubleshoot one model without interrupting drilling. And if there's failed convergence on one of the solvers, you also have the ability to switch to another controller that's ready. Additionally, you have the same benefits that come with hardware redundancy. If you think of pressure sensors or temperature sensors at a certain location, they processes will often have redundant sensors, and if one goes out, you have another backup right there. So with these advantages, we set out to test this controller through simulation. And the simulation that we did used the Syntef high fidelity flow model as the plant that we were controlling. We simulated a horizontal well with a 7,000 total vertical depth, and we make use of a back pressure pump, a main mud pump, and a choke valve. We also, in our simulation, assumed bit pressure measurement using mud pulsing. And in the measurements that would come into our controller and our estimator, we added noise, outliers, and drift. And we wanted to ensure that our controllers wouldn't get caught up in some of the noisy measurements, the realistic measurements that are actually happening. So the goal of the simulation was to maintain the pressure. Now we did normal drilling operations, and we did a pipe connection procedure. And for the normal drilling operations, we had plus or minus 1 bar of the set point. That was our objective, is to keep the pressure within that. And then for the pipe reconnection procedure, it's plus or minus 5 bar. And we do that again by adjusting both the mud pump flow rate and the choke valve. And one of the issues that we noticed in using this ensemble controller is when we'd switch between the high fidelity, or the low order, or the low order and the empirical, we'd get this jerk that would happen, this sudden change from one operating region to another. And the reason why that happens is because each of these model predictive controllers, again, are using an optimization algorithm to find the solution, but they're looking for that solution in different numerical regions. So they're using different numbers to come up with a solution. And so when you switch between them, they jump to where the next controller is looking, and you have this unacceptable jerk, and you can see here how it affected the bit pressure. Well, again, that's a stability issue we want to address and make sure that's not going to happen. So what we did is we took the current drilling process measurements and added those fed those back into the controller, and used those as the initial guess values for for each of the controllers, and that allowed the optimizers to stay in the same general area as each other and to keep near each other. And so you can see here, this is the results of a normal drilling simulation, and you can see that we were able to get rid of that jerk that happened, and it did not. We call it seamless switching because it doesn't affect our bit pressure. And so you can see in these results, the Ensemble controller is this black dotted line, and each of the individual controller suggestions are available and shown. You can see how it switches from one controller to another, and you can see how we're able to stay within the 400 bar set point, within plus or minus 1 bar of that set point. And this is really tight pressure control. This is something that hasn't been achieved. And granted, this is a simulation, but it just shows you the proof of concept that this is a possibility. So this shows the normal drilling. Now if we go to the pipe connection procedure, now during a pipe connection procedure, we lose that mud pulsing measurement. So we lose our bottom hole pressure measurement, and the controller is forced to use only its predictions that it gives from each of the models. And during this connection procedure, there's no need to switch between controllers because you won't have there's no calculations happening during the connection procedure. There's no possibility of failed convergence or stability issues. And so we stay with one of the controllers, and here we use the low order controller. And you can see that the low order controller isn't as accurate. It doesn't match, the equations don't match reality as close as they need to be, and you can see these unacceptable peaks and spikes happening that take us outside of our control region, our desired set point. But you can see this is our valve and how it's operating, and this is the mud pump, both the back pressure pump and the main mud pump, and how they're responding. At this point is when the pipe reconnection procedure started, as the mud pump ramps down, and you can see that just based on its predictions, it does a pretty good job, but it isn't quite good enough. So if we use the high fidelity controller to do this exact same simulation, the accuracy of that model keeps us within our desired set point, that plus or minus 5 bar. And again, here's the valve movement and the pump movement. So again, plus or minus 5 bar is fantastic. That's really great control that these advanced controllers are able to do just using the valve and the pump. So in conclusion, our Ensemble control structure addresses model accuracy issues by using the most accurate model available. It also addresses the controller stability issues, so that if one controller becomes unstable, it switches to another. And using our switching algorithm and our feedback, our seamless switching, we are able to stay within the same region and provide acceptable control. Also, the inherent benefit is the ability to tune and troubleshoot without interrupting the drilling process. Now, some of the future work that we're planning on, and we'll be reporting on later, is we want to use the high fidelity model to tune the empirical model. So that empirical model will converge most every time, but sometimes it gets out of tune when you enter a different operating region. And so we'll use that high fidelity model to tune the empirical model in real time, and meanwhile we'll use the low order model to control the process until that tuning is complete. So I'd like to thank those who helped in this research, those who gave their expertise from Syntef and Huysman, and also the researchers at Brigham Young University and the guidance from Dr. John Hedengren. And we appreciate very much the help that went into this.